Welcome to the robot mapping lecture. Today we are going to talk about hierarchical post graphs. So last week, for the one who were here, we discussed the graph SLAM algorithm, so the graph-based SLAM, which is a way of using a least squares approach for solving the SLAM problem. And today we see how we can extend it in a hierarchical way to improve efficiency and aid data association. So getting back a bit on what we said last time, the graph-based SLAM works in the following way. So we have some measurements that connects that let's say this is a graph here, and each node in this graph, so this blue arrow there, it's a pose of the robot. So we abstract everything in terms of where the robot was at a certain point in time. We have measurements between these poses, so some relative measurements between two poses in time. These measurements connect those poses. We have uncertainty in here, so we do, as usual, we do not assume that our measurements are perfect, but they are uncertain. And those uncertainty comes from either the odometry, like in this case, and we basically are saying that the robot moves forward 1 meter. We will have a measurement here that says these two poses are related to each other by 1 meter displacement, and then we also associate a certain uncertainty in terms of an information matrix on this link here, okay? When the robot moves around in the environment, we also have some what we call loop closure measurements. Those measurements arise because the robot in this pose or in this pose and this pose, so you see these two links here, is observing the same part of the environment. So you can imagine that I'm here, I'm observing that specific column, which is 1 meter in front of me. Then before I was there, and that column was 2 meters in front of the robot. And by considering that the column is the same column, you can overlap them, you indirectly have a displacement, so a measurement between these two poses. And this will be the displacement here and there. Somehow it's getting timed. So once we have these two types of measurements from the loop closure, so what we call data association or loop closure measurement and the odometry measurement, we build up this graph problem by just assuming that each of these is a system of equations, and we have then a lot of equations and a lot of unknowns, and when we put all together, we get an overdetermined system. So we use a least squares approach to find the minimum, the solution that minimizes the squared error on top of the measurements. Okay? Is it clear? Okay. Now, if you want to summarize graph-based SLAM in few bullet points, the first point is we use a graph to represent the problem. This graph gives us a topology or a structure of the least squares and also influences how the least square can be solved in terms of efficiency, because sparse graph results in a sparse least square system, which is more efficient to solve than a dense least square system. We have that a node represents the pose of the robot. We can also add landmarks and other features in this problem. We'll see it later on, so the second part of the lecture today. For now, just focus on there are just poses, which in 2D will be x, y, and theta, and in 3D will be x, y, z plus the three orientation. According if you do Euler angles or quaternion, there will be a different set of parameters. And then the graph-based SLAM just builds the graph. Using this graph, we'll get all these measurements, linearizes the graph, builds a least squares problem out of it, solves the least squares problem, and iterates. Okay? All clear so far? Okay. So, and we also have seen last time that this is all fine, but we need somehow to build this graph, so we need some tools that builds the graph. And when we talk about graph-based SLAM, we basically divide the problem in two main parts. One is called the backend, which is the part that, given a graph and a set of measurements, gives you a solution to the problem, so it tells you where the poses are in the world. And then we have something called the front end, which deals with the construction of such a graph. So it deals with data association issues, it deals with computing these measurements between the poses, and so on. Now, to hide the construction of the graph, and especially to hide the data association, position of the nodes are actually quite useful. And that's because you can limit the search for potential data association by considering where you are in the environment and what are the other poses around you. So you don't want to search for potential matches of poses which are very far away from where you are right now. But for knowing if something is far or close, you need to have a pretty good map or a pretty good solution of where these poses are in the world. So to summarize, we need some intermediate solution, and since we want to have these solutions, since we do data association quite often, we want to have a very quick way to get these intermediate solutions, okay? One idea to get this intermediate solution is to go on in a hierarchical way. So the main intuition behind that is that often to have a rough idea where you are in the world, you don't need to have high precision. So high precision is needed if you need to do some navigation or some very accurate planning. But if you just want to know roughly where you can be in the world, you don't need such an accuracy. So we can just abstract the whole environment. Here it's a simulated sphere where each of these dots is a pose of the robot in the world. And you can just make it coarse up to reaching a single node. So making decision in this type of abstraction is not very useful, but if you are already in something like this, we can already have a limited search, because let's assume I'm here and I'm interested in something which is around here, so we don't need to search all possible data association hypotheses, but just something around an individual node. And we already got a reduction in the problem size from 10,000s of variables up to something about 100 variables. So there is a 1 order of 2 order of magnitude reduction in the complexity. Okay? So that's the main idea of hierarchical post-graph SLAM, where we basically take the whole problem and then we make it more coarse as to hide for a quicker solution to the problem. Of course, these are an approximation, and we'll see now what this approximation means and how we can construct this hierarchy. So the motivation for that, as I said before, is that we want to limit the search for potential data association. So imagine now these situations here where the robot started here, it does a certain loop, and then it reaches this part of the environment. Okay? So if we naively try to look for data association, we have to go through all of these nodes and tries to match the current measurements with the measurements stored at that particular node. No? So that we don't have yet a metric structure of the environment. What we need to, the only thing we have is a certain nodes which corresponds to the pose of the robot, and then in each of these nodes we store the measurements that the robot had from its sensors. So if you have a 3D scanner or a 2D scanner, you measure the points, you store the points that the robot measured, observed at that position. If you have a camera, you can store the images that the robot collect there, or if you have a GPS sensor, you can store the UTM coordinates and so on, or the latitude, longitude, whatever you're using there. So according to the sensor you're using, you're storing the sensor information in the node. For doing a data association between different nodes, what you do is you take the sensor data that you have at the current robot pose, and you try to align them with the one that you had in all the previous poses. Naively, this cost n, where n is the size of the number of nodes that you have in there. But since it's very costly operation, you don't want to do it for all the nodes. So when we try to, what we try to do is that we try to reboot my PC. No, I don't want to. So the robot gets there, and we want to get an idea where the robot is. So we can exploit the uncertainty of our sensor, the resulting uncertainty of the graph, and also the poses there. So we just say, let's try to get a solution to this graph baseline problem. We get the configuration of the nodes, then we look at here and we say, I should be in this location with so-and-so uncertainty, and then we look at what's around the robot with this uncertainty. So we limit the search for data association only in the few nodes which are around the robot. Is it clear why we need such a thing? Any question? Okay. So the inside of the hierarchical approach is that, again, we want to get loop closing points. We want to be very quickly, we want to quickly get an idea of how the map look like. And this is because we want to exploit metrical information to decide where to search for data association. And since we don't care about high accuracy, but we are okay with just having a bit more evaluation than needed if you can obtain the subset quite quickly. So we are okay with having a rough or an abstract or a more coarse representation of the environment. So we only want to correct then not the full map of the environment, but just somehow a topological core structure of this. So once we build this hierarchy, the idea is that we go on top of the level of the hierarchy, we have the coarse topological structure, and then we can ideally, intuitively say, the robot is in this area, and then we go down and say this area looks like this. And so we can still do a full data association with all the poses that we have, but we exploit this hierarchy to get an idea of where to search. It's kind of, you can see it similarly as a binary search or a grid search where you go down. So you first try to get in which beans or big chunk of the environment you are, and then you get everything which is in this chunk of the environment. No? Okay. And of course, this works because it exploits few insight or few characteristics of the problem itself. One is that the robot is moving and it's not teleporting itself. So something which is close by will remain close by. So something which is close by in time remains close by in space. And also that the sensors have a limited range, so I don't really need to try to match something which is too far away from me. Okay, so these are characteristics of the problem, and this hierarchical approach tries to exploit those characteristics. So what's the idea of the hierarchy? So imagine here now we have as an input a dense graph, and this will be our dense graph. We first build we just first group the nodes into locally consistent or local local patches of the environment. And most of the time, those will just come from odometry, for instance. The robot is moving around, and then after a certain amount of space that it travels, you just collect all the nodes into one cluster in this sense. And sometimes you need to exploit also a bit of data association. So when the robot is coming back and you found data association, you then reevaluate this clustering and you just put other nodes together. But in principle, the idea is that we have a method for computing these clusters, which are nearby in space. For each of these clusters, we select a representative node, which is going to be somehow an anchor of the place where the robot is, or as an anchor for the specific cluster there. And then we just abstract another graph on top, where we only use the representative as nodes, and then we compute these measurements from the full graph that was down there, okay? But those are only computed once, so whenever the robot evolves and goes on and the clusters do not change, also these measurements will not change. So it's not that every time we need to recompute those measurements, but we just do it once at the beginning when we did the clustering, and then we keep those values over time. Once we have the graph computed in this way, we can just optimize the graph, okay? And we get a better estimate of the coarse structure of our map. And once we have this estimation, we can then propagate the solution to the other nodes which are attached to the representative. So the idea here is something like this. So if you go back here, you see that there is some displacement from the representative to the other nodes. We just optimize the representative, and then we apply the same displacement that we had before to the new computed solution. Okay? Okay, so this is the insight or abstract idea. Yes?
Yes, I have a question. How to decide which node is representative?
Okay, so the question is about which node is the representative and how to decide it. That's in general, so you can have a set of heuristic. You can, for instance, say it's the one which is in the center of the, or close to the center of the nodes locally, or you can just say it's the first one temporarily in the environment, in the cluster, or the last one temporarily in the cluster. It doesn't really matter. So the whole point here is that you just need to have one representative, and you then, as long as the distance between the representative and the other nodes is not too big, you can get the same results. So it doesn't really matter how different they are. Okay. There are also more advanced techniques where you don't get just one representative, but you completely transform the cluster in a different way. So one, for instance, is that you keep all the boundary edges and you eliminate everything which is inside the cluster, and it's a different problem where you, for instance, keep everything which is at the border, okay, of all these clusters. You keep the same measurement that you had before, and you just approximate inside the cluster. So there are different ways. The simplest one is to take the first one temporally. So if you say timestamp 1, 2, 3, 4, first cluster, then you take the one at timestamp 1, then you have timestamp 5, 6, 7, that's the cluster, you take timestamp 5. Okay? Yes?
If you do the high-level optimization, the representatives, they are usually weakly related, right? Or less strongly related than in the clusters themselves, because they are usually further away.
Yes.
And if you do then the optimization, you assume that you get like a bigger error on the optimization. And if you propagate that down, you work on the low level with like a bad position of your high level optimization. Would you assume that?
So I don't know if I get the question correctly. It's like doing this, you get worse. Yeah, that's true. That's definitely true. And of course, the more nodes you have in a cluster, the worse you get. And that's because of two effects, I will say. One is that so whenever you get a measurement between these two, it's actually not too bad, because you consider all the neighborhood. You will see later on how do we get the measurement between the representatives. So you propagate all the informations that somehow connects them, even if they are not trivially connected. The reason why you get worse is because you lose in linearization. So you commit to a linearization point and you can never revise that. And it might be that the linearization point should change. Therefore, you should change the measurement between these two representatives, but we are not doing it. So that's one reason. And the other one is still on the linearization point problem, that again, these are nonlinear. So if I move something here and then I apply the things, it's not the same as considering the whole chain. If it was a linear problem, then that's not a problem at all, because there are some properties that allows us to say, I can decompose this thing. It's not a linear problem, so it's a bit more complicated to analyze. So in principle, you get an error due to these two different sources. No?
Yeah.
Any further question?
Yeah. The last question is about page 16. You have said only the upper level of the hierarchy is optimized.
Page 16, this one, yes.
And about the first statement, I just wonder how is this optimization procedure like?
We'll see later on. But when you say, so this is when I optimize the upper part, I use exactly what I explained last week. So that's exactly the same optimization technique. It's the same problem. We have poses, we have measurements, virtual measurements between poses. It's the exact same problem. The only difference is when we get on the lower level, and once we get to basically the lower level, instead of re-optimizing it, as we should do, we just apply this transformation. Okay, so we store how far these things are, and then we apply them. So let's go very simple example. Okay. So imagine a situation like this. Now, this is the graph, and we say this is one cluster, and let's say this is one cluster. Okay. So, and I choose these two guys as representatives. Okay. Now, let's do the easy thing. Let's say this becomes something like this on the upper level. Okay. So, and we can imagine that we just take directly this as a measurement. It's not the case because this edge and all this will actually influence, but let's assume it's simple. By simplicity, it's just this one. What will happen is that these are our representative. We solve this for the representative, and then we propagate the displacement. This basically means that for the solution of this one, we propagate here. The solution of this two, we propagate here. So that's basically what we are kind of losing from, instead of solving the full graph here, we solve something like that, where part of these chains are included in this link, but not all of them, and then the other part is actually lost. So I don't know if you get the picture here, but that's somehow the idea. It's kind of like we're changing the topology, we're changing the amount of the sources of information and measurements, but we are getting something close to what we had originally. Okay? Any further question? Okay, so then we can go on the more technical detail. So there are a few questions when we build this hierarchy that one needs to answer. The first one is when and how we generate a new cluster. Normally, you can build any complex heuristic or whatsoever you want, but actually the best choice and the simplest one, the best choice is still the simplest one. Since we are building this graph incrementally when new observation comes in and when the robot moves, we just simply have a distance-based threshold. So we say a cluster cannot be bigger than X. At some point, you close one cluster. Or if you start from the beginning, you assume that you have a closed one cluster. You take the first pose as the origin of the cluster. You travel as long as you are further away than X. Then you close the cluster, you start a new one. No? Very simple. The second thing is how to propagate the information downwards, or actually when to propagate the information downwards. This basically means when do we rebuild the cluster? When do we rebuild the graph? So the whole idea here is that we have this coarse level, and then we start off optimizing this coarse level over and over, and we just approximate ever and ever and ever. Now, there is a point of, do we still stick with this approximation all the time or not? And one idea is that once in a while, rebuild the whole structure again, rebuild the whole hierarchy again. The reason for doing this is that since we are doing it once in a while, it's not so computationally expensive. It's amortized all over the life of the robot operation. But this allows us to keep this whole hierarchy kind of focused in place so that we do not accumulate too much approximation error with the hierarchy, and then we defeat the whole idea of things which is close by will stay close by. No? One clear example is when you do, for instance, a loop closure. When you do a huge travel around, and then you come back to the initial location of where the robot started, of course, this is not there any longer in your map. No? So all the information, all the measurements between the initial pose, so at time 1, and the pose at time 1000 when it comes back, they are not used. These two nodes are not in the same clusters because one has been built already and it's pulled apart, and then I have now another cluster which is built already and it's put apart. And it's a good idea to in these situations, to just rebuild the whole hierarchy from scratch, no? So that you still keep this connectivity in the lower level. This is just an example on when it makes sense, and what we actually do normally is that you check for consistency in between the two hierarchies. So you check for the, if I have a data association in the low level, what happens with this measurement when I propagate it from top down? Is it still statistically consistent with the real measurement? If it's not the case, then you restart everything. Okay, so again, it's another decision that you have in the whole construction of the hierarchy that helps you to keep the approximation error lower. One doesn't need to do it, it's just a way to help in the in keeping this error down. And having a limited error helps because it reduces the effect on nonlinearities, it reduces the effect of data association errors, and so on. The other two things which are actually more important than that is how we construct the edge in the sparsified graph, and also how we then propagate the information downwards. Okay, so how we put the things down in the different nodes. So how do we do the edge? So since we are connecting two clusters, so we take these two representatives, the red one, and we also take all the nodes in the cluster together, and we would like to obtain a new virtual measurement Z between those two. Okay, so the only information that we have locally between those two clusters is somehow given implicitly through the connections that we have with these other nodes. Any of you has an idea how we can do it? So we just need to have a Z, so a measurement between these two nodes, which are these two nodes, that depends on all the others. Any idea? Anyone wants to try? So what can, imagine that everything is solved and everything is fine, no? How would you get a measurement between this node and this node? Well, let's do it easier, no? They are like this, no? This is my representative, this is my representative, and this is my graph. How would you get it? You probably just take the information on this node, right? On this edge. You just take what's in here and you say that's the same. Now, if you imagine we have something in between, no? Yes?
Assuming we have already solved it, we assume that it's linear, so we just do like two linear transformations from one point to the intermediate node and then to the other node. And then we have like the linear function between the two percentages.
Okay, yeah, that could work in this case. I mean, we don't have we can also just compound the different transformation as well, no? So we can also say the mean will be the application of the function, one and there, and the covariance we do with the linear transformation. That's fine. But what if we have now this case here? So there is not only one path that connects these two nodes, but there's also a second path that connects these two nodes, which is the more generic case. Huh?
Maybe do the weighted average, and the weight is dependent on the covariance matrix.
Yeah, so we can do a weighted average. That makes sense. Is there another way of generalizing the weighted average in some way? So what does the least squares problem solve at some point? Any idea? I think so. You're getting close to that. Now we can do a weighted average, right? But then I mean I can add any potential other paths. For instance, I can do this, no? And then I can add any potential structure in there. And then the question of how many paths are there and how we can do the weighted average is not clear because they're not independent, no?
You can make again a least squares problem and solve only for the two nodes.
Exactly. So you can just solve another least square problems out of that. This gives you a solution of between them, and this also gives you the so you take the solution for these two, and then this will be our mean, and then you invert your Hessian, you take your covariance between them. And to make things easier, you just, since we need to fix one of the two when we do an optimization with relative measurements, we can just fix one of the two. No? And that's how we do it. Okay? So that's exactly, I think the next slides will probably just say this one. Yeah. So we optimize this, then we take the values of the two, and the observation is from the mean. So you take the solution for this two and take the difference, and the uncertainty is taking the inverse of the Hessian. We just take the block which is at the, in this case, BB, in the sense that we fix A, then we take the marginal uncertainty, which we need to invert our Hessian, take the marginal covariance, so the block at BB, and then we reinvert it again because we are, what we want is an information matrix and not a covariance matrix. And we can easily invert these matrices because the size of those graphs is not that big, and it's not the problematic in terms of computational, they're not computationally expensive to compute, okay? Is it clear how we do it from the full problem to the two clusters, and then how we get the measurement between the two representative? Any question? Okay. So, how do we propagate the information down? This is actually easier in some way. So we know that each of these nodes is always the same one. So we have a connection between the coarse higher level structure and the finer lower level structure. So all the representatives in some way are node from the lower level. So we just basically propagate the information down in using a rigid body transformation. Okay, so we are saying x and xa are there. I remember the measurement before, so this and this, and we just apply the same one down. Okay, so that's what I also said before. You just consider this as the origin of the word. You just have the relative transformation and you apply them. And one thing to consider is that right now, as you can see in the image, they kind of got closer and so on. But the important thing is that those links are actually not used any longer. So when we propagate the information down, the measurement, the intercluster measurements are not considered any longer. No? And that's where you can also check for inconsistency when you want to know if something went wrong in your approximation. No? Because you can say, I propagate everything down. This means that those two guys are now in a certain configuration, and they should be they should follow a certain measurement, which is has its own mean and its own covariance. And you can check how many of these measurements are actually violated, and then you can decide, oh, I violated too many measurements right now. I need to reconstruct everything from scratch. So that's what when I was saying before, when to propagate and so on. That's when we do the propagation and rebuilding of the graph. Okay? Question on that?
Sorry.
Yes?
What do you mean by the observation violation?
So let me see if I do it. No. Yeah, that's what I mean here. So the idea is this. Let's see how I can. Probably this one is the easy one to do again. So I will just redo it again. And it was something like this, this, and this. And then we put one thing here, easy. Okay. So imagine we are in this case, no? and again we go down, and right now we just have a very tight measurement, and we'll end up in something like this. No? So this one here will be the same measurement there. Okay? Now we can take the value of this guy, and let's say this tells us these are 1 meter apart. Okay? And we can also consider the uncertainty in the estimate, and we say the, I don't know, like plus minus 0.5 standard deviation. I'm just putting numbers there. No? Now we get the original measurement, and this will say these are 10 meters apart. That was the original measurement. And yet somehow plus minus 1 in standard deviation. Okay? Now, I'm not really sure if these numbers make sense of what I mean, but let's say if you take this measurement here, okay, this will have a kind of distribution like this. Here we have 10, and say it's a Gaussian, and it's like this, no? And now we say, we now put this guy here and see what's the, how consistent is this? And let's assume it's here, no? That's like the one is there. This is very unlikely, okay? So having something which is on the tail of a Gaussian distribution is very unlikely. We have the usual thing of sigma, 2 sigmas, maybe it's 3 sigma here. So we got a value which is far away than 3 sigma. It's almost never, it's really a very unlikely event. And if you have a lot of these unlikely events, then something went wrong somewhere. That's the whole idea there. That's what I mean by when we see inconsistency, we can recompute everything from scratch.
And so the upper part is already after optimization.
The upper part is the original graph. This is the original graph. I take my clusters, I take the representative, I optimize just the representative, I get a solution, propagate from these measurements here, and then I check the consistency of the one that I'm not using for the optimization. No? Does it make sense? Okay. Yeah, that's where the arrow is pointing at, so here. All right. Any further question on that? No? Okay. So now the last thing to do before we go, I'll show you a bit of how it works in practice, is when do we get the map? Now, so if you want to get the best possible map out of it, we will not just optimize this and go it down, but what we will do is that once you finish processing your data and you want to get the best thing out of it, we will just take this solution here, we propagate everything down, we put back all the measurements that we eliminated, and we just optimize the full graph from scratch, okay? So with this new initialization. Now, one can say, does it really matter if we start from this or if we start from the original data that we got? The point is it does matter because for two reasons. One is that we are starting with something which is hopefully close to the minimum. So we are not wasting the computation that we did so far while collecting the data, optimizing. It might be already in a good shape. It just needs to be moved a bit here and there, no? So that translates to I need less iterations for the full problem because some of the iterations I already did it in the past while I compute when I was optimizing the hierarchy, okay, the upper level. And that's one thing. The second thing is actually, it's not written in here, the second thing is quite interesting. It can happen that you get better maps because you end up in a better minimum, okay? And the reason is that when you have too much data, you get a very shaky cost function, no? Because each of these measurements will add a small peak in your cost function, or if you see it the other way around, a small minimum in your cost function. And when you eliminate some of these measurements without destroying the whole topological structure, you remove some of them that do not make too much sense. So it's kind of, Let's imagine this. Imagine that you have something which is like this. Okay, so that's your cost function, I'm just assuming. And if you have a lot of measurements, it might be that if you start here, no, you might be stuck down here. No, so you don't reach the real minimum, but you reach a local minimum. Now, if I try to get a bit of coarseness, so I just throw away some of the high frequency measurement or some of the one that makes all this jiggly, but they keep the same structure. Somehow it's like you're getting a different function, no? So maybe you're getting something like this. You optimize with this and you end up in a minimum which is somewhere here, no? So it's still not the correct one, so it's still not exactly where it should be, but it's close by. And then when you project it and use it as initialization for the previous cost function, the full cost function, you are closer to the global minimum, and then you're able to reach it. Okay, so that's kind of tricky to understand if you haven't done a lot of optimization and you haven't played a bit with that. But the whole point is that you kind of relax the problem, you make it a bit easier, but keeping the same topology in the cost space. So, does it make sense? Any question? Okay. So then how does it work in practice? So let's say, let's have a look at a couple of data sets on how it works. So this one is a parking garage at Stanford, and the robot was a car in this case and was going around and then going on top of the parking garage. It was a very long run, a lot of data, so we want to do it real time. We needed to find a way of efficiently computing everything. So this is the final map built. Here you can see a video, hope it will work, where on top you see the full graph, so using all the data, and off the bottom you see level 2, so like 2 level of abstraction. So what I didn't say before is that you can build as many levels as you want, and each 2 level hierarchies you treat it as in the same way. No? So once you have a graph, it looks like a graph in the bottom, and you can keep on going up and up. The important thing to see here is that although let's say the map or the metric accuracy of these nodes is not as precise as the one up here, the topological structure is still there, no? And that's what we care, because we want to know if the robot is here, which nodes to consider for data association purposes. And you can see, sometimes you can see that something is changing and flickering around. That's because it's the result of either optimization in here, or can also be the result of recomputing the full hierarchy once something gets inconsistent. No? So, as you can see, for instance, here is jumping a bit around. And now you can see that it's really like way less nodes and way less poses stored in this level, but still we can get something out of it. And then when we go from here, we just propagate back everything, you optimize, you get something like that. Okay? Another data here is the Intel lab. It's an indoor data set. And you can see here now level 0 and level 2 are on top of each other to get an idea of how precise the 2 levels are. As you can see, the blue line is almost every time on top of the red line. You can see that sometimes when the robot does loop closure, it's not creating new edges. That was one case, for instance, but it's just rebuilding the clusters because there was an inconsistency, and then it just rebuilt the cluster with the new nodes at that, put it in the old clusters. Now the same thing is happening here and there. So as you can see that the backbone, the topological structure is quite correct. Some nodes are actually almost in the exact position, some representative there. But what is actually really important is we can use this structure to do some efficient data association query, and we do not lose much in terms, so we don't lose almost anything in terms of data association capabilities. We just lose a bit in accuracy, and we'll see now how much accuracy do we lose. So the last thing I want to show, and then we can do a 15 minutes break, is that how do we actually perform? So the whole point here is can we evaluate the performance of the hierarchical approach with respect to the full-blown SLAM approach, and does it really make sense to use it or not? So intuitively, yes, it works, it makes sense, but in practice, we can actually compute the masses of the distributions which are not covered, okay? So the idea here is that we can get an estimate of the final map in terms of the estimate of the final poses, and then we can check if the probability mass of the true solution is inside the mass of the approximation and vice versa. Okay, so how much of this is covered or not? If you look at it from, let's see it in 2D, we can imagine a phenomenon like this. We can say one estimate is, let's say, this ellipsoid showing like this, and then we can say I now get another estimate which is maybe like this, no? And we can say this is the part which is not covered of the true estimate from the approximated estimate. And this basically means I might do some wrong decision, okay? Because if I do a decision based on my estimate here, I'm doing something wrong. And wrong is bad in this case. Or there is also a part which is, let's say, bigger than the original one. This is not too bad, because this basically just means I'm making a mistake, but I'm underconfident. So I'm underestimating the thing, which means I think I'm worse than where I am. And what will happen if you make a decision on in these cases is that you will consider the association hypotheses which are too far away to be true. But in practice, what will happen is that if they are too far away, also the environment will look different. You will not manage to get valid association hypothesis by looking at the sensor data, and you will discard them anyway. So the only negative effect is that you will need to consider more hypotheses. It's a bit slower, but that's the only effect that you have. So it's not a drastic bad effect, but it's still a slight negative effect. Being overconfident, so not covering the full mass, it's bad because you are omitting good associations, okay? And we can analyze from the different, from several data sets what is not being covered and what's outside. And the interesting aspect is that generally we are not too much overconfident, okay? So the mass of the distribution covered, so not covered, is very low. But we are a bit underconfident in some way. So the estimate is a bit larger than usual, which is not too bad, and it also makes sense in some way because part of the information has been thrown away, part of the measurement has been thrown away. That makes the whole estimate a bit more uncertain. The reason of this is that the problem is nonlinear, so this covariance is actually can rotate a bit, and therefore you get a bit of not covered area because of this rotation, or also because of maybe a different minimum where they converge, so on, because it's being a nonlinear problem, it's kind of complicated to do some statistical analysis on that. If you want to get an idea on the Intel dataset, on how they look like, you can say that a red here is, for instance, overly confident, and the blue is underconfident. And we can see now here in red is the original estimate from the true estimate with all the data. In green, we have an estimate at level 1 of the hierarchy. And in blue here, we have an estimate of the level 2 of the hierarchy. And you can see that there is a bit of overconfidence here in this area from the different estimate. And there is then a bit of underconfidence in this area. And this is something which is evident in almost all of these cases. And as you can see, everything has been shifted on the right. So this already can give you an idea that what happens is that the estimate is a bit of a right bias. And probably because we're not considering the measurement that puts these things together, or this puts them apart a bit more. No, so it's clear that you have the same effect every time. So there's a shift on the estimate on that. Okay? So conclusion is what I've shown today is an hierarchical approach for graph-based SLAM, which helps us in terms of efficiency for data association, and also is not and it's often good for online mapping, and shown that can be used to interplay a front end with the back end. Then also that the higher level representation simplifies the problem, makes it easier to compute, quicker to compute without losing too much into accuracy. There's a bit of literature on that. You can see the link on the web page as well, so you can get more technical insight on this. And we can do a quick break of 10 minutes and we can start at 15 again. So welcome back. So the second part of the lecture today is about graph-based SLAM again. So basically this will be somehow the topic until the end of the class, graph-based SLAM plus something. And right now is the plus landmarks. So far we just saw how graph-based SLAM can be applied to pose graph, so where the nodes is just a pose of the robot, and those poses are connected by measurements, and those measurements are sometimes virtual measurements, so that they always have a full observation between these two poses. They all have a relative transformation between them. Now we are going to see how we can handle landmarks, where landmarks are just points in the environment, like stars or pillars or corners, or everything which is somehow can be represented as a point. And we'll see that these actually are not, with one landmark you're not able to get the full pose of the robot. There are some observability issues, and we'll see how we can handle these observability issues. So again, graph-based SLAM, we need to somehow change now the definition, because before we just said that every node corresponds to a pose of the robot, and now we're going to extend it by saying that every node can correspond either to a pose of the robot or to a landmark in the environment. Every edge before was between two nodes and always corresponded to a spatial measurement between them. This is still the case, but now we have different type of measurements. We can have like bearing only, where we just measure the angle between a robot and a landmark, or we can have range only, or we can have range and bearing. So according to which type of sensor we are using, we can have different measurements between a robot and a landmark. And again, we still have the same approach. So we have a graph-based SLAM. Each measurement is an equation in a least squares problem, and we try to find the solution that minimizes this solves the least squares problem. Okay. Now, let's stick on the 2D case, which is easier. So to get more into the detail, we only had robot poses so far, so x, y, and theta. And we always add virtual measurements between poses. So we basically were implicitly considering landmarks, but just including the information of the landmarks into measurements between poses. For instance, when if you consider laser range finder, they have a lot of measurements. You could consider each of these point measurements that it's returned from a laser scanner as a potential landmark. You could include them in your graph, and then you just need to do data association between these point-wise. Or you can abstract everything and say, I have a set of landmarks from pose 1, I have a set of landmarks from pose 2, I can triangulate these landmarks together to align them, and then I get the virtual measurements between the poses. Okay? So that's the approach done by pose graph. And right now we're just trying to say, okay, let's assume that sometimes you don't have enough landmarks to get the virtual measurements, so you need to put these landmarks directly into the optimization framework, okay? And that's where we are going right now. Landmarks, you should remember them from the beginning of the class when we were talking about the Kalman filter and the origin of SLAM. And probably this picture, you should look familiar. Imagine that this is the robot, our vehicle, and we have some pillars around which are our landmarks. And Everything is measured with respect to global reference frame, so the pose of the vehicle is with respect to the frame, the position of the landmark as well, and then we can have some observation which is either the relative angle from which the robot observed the landmarks, the distance and the angles, and so on. Okay? Another type of landmarks in the real world are, for instance, tree branches. You can imagine tree trunks. You can imagine that each of these trunks can be detected from either a camera or a laser rangefinder, and then you can assume that those are just points in your world which has a certain diameter or so if you wanted to use the size also for data association. But in principle, you can get the center of the trunk and assume this is a point, or abstract this as a point in the real world. And I think we also saw these figures when we were talking about the Kalman filter and the fast LAM. So landmarks have been used a lot in the community because it's a very nice abstraction of a material point in the world. Okay? If we now go from the real world to the abstraction of graph-based SLAM, we have something very similar to what we've seen so far. We have the poses of the robot, again with the blue triangles. We have our measurements in orange, and there can be now measurements between poses. So nothing changed. That's the same thing that we've seen in the previous lectures. Or we can also have measurements between a pose and the landmark. And that's what we are going to explain right now, how we can model this and how we can then solve the problem with those things in there. In general, when we talk about graph with landmarks, we do not have explicit data association or loop closing measurements between poses. Okay? The reason being those measurements, they normally occur because we take some of the landmarks out by aligning them, and we don't want to do this right now here. And the second reason is that for simplifying things, we just consider data association on the landmark level. Okay, so the only data association decision that we do is this landmark that I'm observing right now the same as one of the landmarks that I have in my map? Okay, so one can still add loop closing measurements between poses. It's not a big problem, but they will be treated as in the same way as there will be odometry measurements or incremental measurements. Sometimes it's good to have them because you can have multiple sensors, and you can imagine that you use cameras only for getting the landmark-based SLAM and the laser scanner for doing the full graph-based SLAM. So it's fine, and it's a nice way to deal with the different modalities. But for now on, we just assume that there are two types of measurements between poses and between a pose and a landmark. Okay? Any question on that? Okay, so this is the graph we're considering right now, and we have this again summarizing these two types of nodes. Stars are landmarks, arrows are robot poses, and we have these two family of measurements: odometry, we call between robot poses, and landmark measurements between a robot and a landmark. So mathematically, we consider a landmark as a point in the world, so it only has the x and y coordinates. There is no orientation of the landmark. One can also extend this to landmarks with an orientation, but then there will be no difference than robot poses and landmark. Okay. The interesting part is when the orientation of this landmark is not obtainable from the sensor. And we also have relative observations in x and y. So we can have, for instance, an observation that tells this is at x and y away from the robot. Or you can say it's 3 degrees on the left and 4 meters forward in that direction. Okay? So this is the kind of observations that we are considering. Imagine now we have an XY sensor. So in this case, the robot knows with respect to its local frame that the landmark is 3 meters on the right and 2 in front. Okay, so it will be somewhere around that. This is the same as saying that the landmark is at, I think, 60 degrees and I don't know, the distance where it is, like 5, let's say, far away. So for this case, we just consider it that there is xy measurement. And this you can write it like this. You have xi is the robot, so this is the expected measurement, the one that we compute from the state space, where the state space, one part is the robot pose at a certain time, and one part is the landmark. We get the robot xi, so the robot pose at times I in this case, and the landmark xj, so it's still part of the state space. What we do is we take a difference between the x and y of the landmark and the transitional part of the robot, and then we need to rotate it with respect to the robot pose, okay? Because all of this is in x and y coordinate, okay? Does it make sense? So this is there, we rotate it according to the robot, and that's where the real global coordinate is. Right? Question? Okay. Again, once we have these predicted measurements, we can find out which is the error function for this specific measurement. And we take our expected measurement z hat, which is the one we compute up there. We take the real measurement, so the one we take directly from our sensor, and then we take the difference out of that. Okay?
So what's actually the robot translation? Could you please give a...
That will be the x and y of the robot. So let's go here. So this is the nice global reference frame. Okay? Here is our robot. Here is our landmark. Okay? So the landmark is at x, y. The robot is at tx, ty, and then is rotated of theta. Okay? So the translation, ti is this vector here, and the pose of the landmark, the position of the landmark is the xy. Okay? So it's where the robot is in the world without the rotational part. Okay? Since the landmark is only a point, we can also have a different type of measurements, which is less than the xy measurement, so it's even a rank less, an information less, which says I'm only observing the angle, and that's called the bearing only observation. This is important because that's the type of measurement you get from cameras. Okay, so you can imagine that you can see cameras as bearing only sensors because they normally have no idea on the distance or how far something is from the projective plane, but they just have a ray that goes in a certain direction and it gets the luminosity of that specific area back. No? So like light hits something, comes to the camera into a certain direction, you get the color in this direction. If you have a stereo camera, you can triangulate and get a distance, but if you have a single camera, you can only get an angle. You can try to hallucinate distances by saying, this is something that belongs to a car has a size of this because I know, and so on. But in principle, geometrically, you only have an angle measurement. Okay? So the robot basically observes the angle towards the landmark. So it's staying here and says, I'm seeing something on that direction. And so we can project or predict the robot measurement by just saying, taking the difference vector. So if you go back on here, will be this vector here. Okay. Now, once we take this vector, we can take the arcotangent of the sine and cosine in this way. This will be like, this is our nice triangle. The coordinates x and y will be the x here, the y here. We just do the arcotangent of that. We get the angle from here to there. Okay, so let's call it alpha. And then we want to remove, actually, we should get the angle. Yeah, no, that's correct. We want to remove this theta here, okay? So we just want to get, this is the orientation of the robot, we just want to get our theta hat there, okay? Because then which means we work in global coordinate, we take the angle of this ray where it's been seen by the global coordinate, we subtract the orientation of the robot, we get the expected angle from the sensor, okay? And that's what's written here. And again, we assume a linear error, so we take linear after that, so we just take the difference between the expected error and the expected observation and the real observation out there, okay? So these are the two main class of measurements that we use for landmark-based SLAM. There is a third one which is not that used, but it's getting more popular. It's where we just have distance measurement, but no angular. So which will be the, on the other spectrum of this bearing only, will be distance only sensor. And the reason it's getting popular is because it's what you can use for Wi-Fi signal strength, for instance. So if you have something which tells you the signal strength of some emitters is that big, you can kind of get an idea how far the transmitter is, no? Because you can imagine the signal gets down after a certain distance, so it's with the square of the distance decreases, and you can somehow get an idea on how far the emitter is. No? So that's why it's getting a bit more popular. But we'll skip it and we'll just go with the classic bearing only or range bearing sensors. Now, don't know if you remember from last lecture, but one thing which was very important was this analysis of the rank of the Hessian matrix for a least squares problem. No? That's because if we have a low rank Hessian, there is no way we can find a solution to the least squares problem because we have an infinite of solutions. So we need to include additional constraints or additional regularization terms on our optimization problem. Regularization terms basically means we need to characterize in the space of infinite solution some solution that we like, which can be the solution of minimum norm, closer to something that we know, or considering that one pose is always at 0, 0, 0. No, so that's what we're doing for the graph-based SLAM. Now, the problem here is that differently than graph-based SLAM, we do not know in advance the structure of this Hessian. For graph-based, for post-graph, we always said we only have relative measurements, so it's a very clear structure, and we can then compute the rank and see that there is only a 3-dimensional in 2D problems or a 6-dimensional reduction in rank. We can fix everything with the one pose, and we get then a full rank system again. For landmark-based, we should consider all possible combination of all possible different landmark measurements with all the poses to get an idea on where why there is a rank deficiency in the Hessian, which is something that it's not possible to do unless you have all the data, and it's very computationally intensive. So there is a different way of doing this, but right now I just want to get you an idea on how the rank of the H for these 2D measurements looks like. So imagine that when we do the landmark pose measurement, sometimes you can see constraint in there. I don't like them, but just to get why it's in here. In literature, constraint and measurement are used in, let's say, interchangeably. So you can sometimes hear people saying there is a measurement between two poses, or there is a constraint in the graph between two poses. It's a bit misleading because in optimization, a constraint is something that is just yes or no, while the way we use it in least squares minimization is something that should be close by, no? So like it's a random variable with like normally a Gaussian random variable centered in the value there. So it's more like a soft constraint. I like the measurement word. If you say constraint, it's fine. And sometimes I even forget to write measurement and write constraint. Anyway, the idea here is that if we take the two, the landmark pose measurement, the full one, so x and y, we know that we have two variables on one side, on the landmark side, and we have three elements on the pose side. No? So our Jacobian will be a 2 times 3, okay, because we have the two values of the observed measurements of our z, and therefore the Hessian for this specific measurement cannot have more than rank 2. Okay, the reason is that this is a fat matrix, and there is a 2 times 3, so it must be, the third column must be linearly dependent on the first two, so you only have 2 as a maximum rank of the matrix. So if you take, you can also see it differently, that the rank of A transpose A is equal to the rank of A transpose of, or the rank of A. Since the way we build H is A transpose, in this case J, okay, will be J transpose J, or J transpose omega J. Omega is full rank, so we can remove it for now. This is the same as the rank of J transpose, or the rank of J. J is 2 times 3, so the maximum rank is 2, therefore the maximum rank of the Hessian for this measurement is 2 as well. Okay? So what happens when we have a Birringoli constraint or a Birringoli measurement? What's the rank of H? I mean, we can do the same reasoning. The landmark pose, we had the 2 times 3 matrices because the observation was 2-dimensional, the pose was 3-dimensional. What happens in the Birringoli measurement? Any idea? How does the Jacobian look like? So we are measuring only one thing, right? Which is the angle. So it must be 1 times 3 again, right? So how will be the rank of H then? Will it be 3? Will it be 2? Will it be 1? Okay, yeah, it's 1. It's the same reasoning that we had before. So we are only observing one part of the state space. We're not observing the full state space. You can also do it actually geometrically, no? So imagine that the robot observes now the landmark xy. So he only knows that the landmark is 1 meter on the left and 1 meter in front, no? And assuming that we know the landmark is here, where the robot can be? Where can the robot be? Any idea? And the only thing I know is that that chair, so the corner of, no, let's say the corner of that table is, that's somehow like 1 meter on the left, and more or less 1 meter on the left and 1 meter in forward to me. So I can of course be here, right? Can I be here like this? Yes? Can I be, don't know, here? So what's the, then, where can I be? So where can the robot be and how this solution is constrained? Any idea? Will it be like a straight line down here, a square, a circle? Any idea? Okay, so the robot, let's do it graphically. So here is the landmark, and let's say here is the robot, one possible robot, and the landmark is 1 meter here, it's 1 meter, so let's say now it's 2 meters, 1 meters. No, that's one possible thing. But I can always take this and do like that, no? So when the robot is here, or let's put it here, I can still say that's the distance. From the robot point of view, this is again 1 meter, and this is 2 meters again, no? So basically, what's happening is that the robot is on a circle around the landmark, whose distance, whose radius is the the distance of this measurement vector, so the norm of the vector that is measuring. And the other thing that is constraining is the orientation of the robot, okay? So whenever I am there, I can, it's a bit strange to do it, but I have to keep my orientation while I'm going around to be on the same relative orientation with respect to the landmark, no? So it's basically saying the space of all possible solutions from one landmark and landmark pose measurement is around this circle, and plus we have a constraint here that says the robot must keep the same orientation relative to the landmark, okay? So that's what happens there. So you can already see that if you just have one landmark and a set of poses, you cannot really say anything about that. So there is a lot of ambiguity where the solution can lie. We say it's a 1D solution space because there is only really one element that we need to figure it out, which is which part on this circle coordinate I am. Because once I have it, everything else is defined. The x is defined, the y is defined, and the theta is defined. Okay? You can also see it in a different way. I have a 3 dimension that I need to find, x, y, theta, and I only observe 2, which is the x and y relative to the landmark. So the landmark is fixed, I always observe 2 of them. Therefore, one dimension is free to go. Okay? The same thing you can say if you have a Birringolli sensor. It's now the robot can be anywhere in the xy plane, but there is one thing which is constrained. And do you want to try to find out? So it can be everywhere in the plane. Yeah.
With the orientation.
Exactly. So the orientation is constrained by the fact that it's observing this landmark from a certain angle. And in this case, it's a 2D solution space. Again, because we need to find x and y, and once we have them, we have a fixed solution for the angle. Or you can also see it because there is a 3-dimensional space and 1-dimensional observation that I have. Then the rank connects with the same reasoning here, because the final rank in a landmark-based SLAM is less or equal to the sum of the ranks of the constraints or the measurements. It's less or equal because it can be that several measurements are actually affecting the same part of the state space. So they do not count in terms of final rank of the final action. So it's a bit hard to find and to be sure to be able to find a unique solution, because we need to ensure that this H here is full rank. The way we do it is, before explaining it, let's just figure it out a few things. So we can have some special cases where we know at least how many measurements we need to get a full rank system, or at least a full rank system given that I know I fix either one robot pose or one landmark to 0, 0, 0 to find my initial reference frame. But so if we have only 2D landmark observation, no? And how many landmarks do we need to find the robot pose? So we've seen that 1 is not enough, no? Because with 1 we have 1D solution space. Are 2 enough? Yes? No? Maybe? Who's voting yes? One person. Who's voting no? No? So how many?
I would say 3.
In 2D?
In 2D. I would assume that you have like 2 circles and they're intersecting.
Mm-hmm.
And then if you have 2 measurements, you still have 2
Yeah.
solutions.
Yeah, I mean, it depends, because sometimes you can have it that it's exactly at the border, no?
Yeah.
But yeah, in general, you need to have at least 3 so that you can triangulate where you are. Biringoli, any idea how many you need? One, two, three, 4, 5. Okay, so you should be okay with 3 because you basically can, I mean, 3 is fine, but they need to be in a specific configuration. It's basically like with 3 points you can make a circle, no? And you will be in the center of the circle. But if the 3 points are on a line, then you can't do it. No? Does it make sense? Okay. Now, let's see how we can actually solve the problem of being sure that the matrix is full rank. What you can do actually is you can just add something on H. Now, the problem here is now that we normally try to solve this equation. When we go into the normal equation for solving a least square, we compute our nice H, we compute our nice B, we put the gradient to 0 of everything, and we end up to find the increment over our variables, so the delta x, is related to the H and B linearly in this way. Okay? That's the classic standard iterative solution for the Gauss-Newton, for instance. The problem is now H is not full rank, and we do not know how to make it full rank by just analyzing the structure, because it's very complicated to analyze the structure. What we do is just we regularize it, so we just add a damping factor, which is something that summing up to H increase the diagonal of H, and if this lambda is big enough, then this the full H plus lambda I is full rank. Okay, so you can imagine that if you have an H which is not full rank, basically you can transform it in a way that there is 0 everywhere in one column and one rank if it's one less, and you basically this will just add a bit of ones on the diagonal there, small numbers there. This thing is called Tikhonov regularization when you consider this as a variable, but in general is used quite often on this problem. And the reason here is basically the effect of doing this is that you're trying to find solutions that puts the, let's say if you have like Biringoli measurements, tries to put the landmark as close as possible to you, or just tries to dump the result. Another way of seeing it is that you're doing a bit of Gauss-Newton from the H as an algorithm, and you're doing a bit of gradient descent because you're just using the gradient to update the solution space. So if you remove H, you will just have lambda I delta x minus B. And if you remember, the minus B was computed by getting the Jacobian, the information vector, and the error term. No? So that's exactly what you do if you want to do gradient descent. Jacobian tells you the direction of the gradient. The error multiplies the gradient, so you know how deep you have to go in there. And then you have the lambda that somehow modulates how far you want to go into the gradient. No? So that's somehow the effect that you have there. This algorithm, or this way of solving the problem, actually is not super new or novel only for SLAM. It's actually one of the standard way of solving a nonlinear problem, and it's called the Levenberg-Marquardt algorithm. So it's in the core of the Levenberg-Marquardt, and there is also a way of knowing how to compute the lambda there, so how to increase the step size, it's called, or the damping factor, and there are several other heuristics in there. But in general, you can see it as a weighted sum between the Gauss-Newton step, which requires a full Hessian for doing that, and a gradient descent step. And the gradient descent does not require to be to have anything in full space, because if there is something which is not observable in some direction, the gradient will just be 0 and will just stay at the initial guess, basically. Okay? The full algorithm for the 11-layer Marquardt, actually in the simplified version, is expressed here in this pseudocode. So if you remember before, we didn't have this part. We still had to build a linear system for the Gauss-Newton for SLAM. We computed the error. This is still the same, so we keep the previous solution. When we solve the sparse system, before we didn't have this lambda I, we just have h delta x equals minus b. And then we add the update for the delta to the estimate. Okay, so that was the Gauss-Newton. Right now what we are adding is an initialization terms for the lambda. So the damping factor is initialized according to certain value. Normally it's initialized to 1, but you can change it. Then when we solve the sparse system, we include this damping factor there. And then we check if the error has been decreased. So if I'm getting actually better in terms of solution, then I will increase the lambda, because I want to go there faster. And otherwise, if I'm not improving, it means the gradient is bringing me in the wrong part, and then I'm reducing the lambda. Okay, so that's the that's the idea of this. So this gives you a concept on how to update the learning rate. You always multiply by 2 or divide by 2 according to how you are evolving your optimization step. Okay? Any question on that?
Is the pseudocode, the E is always assigned equal to arrow x. How can this conditional judgment of E is not?
Yeah, because x changes here.
Oh, okay.
This is the old error before. That's the error before you solve the system with the increment. And that's the new one, and you check if the previous was smaller than the current one. So if I got worse, increase lambda, otherwise reduce lambda. So that's what it says. This is the previous error. If the new error is bigger than the previous error, I did something wrong, I increase lambda. Okay, so that's the pseudocode. There are several other ways of doing this, and there are also a lot of other families that are similar to that. They all fall into the category of trust region methods, where you basically try to build a region where you can trust the convexity of the problem. So this is something like I use my convexity, and that's somehow like the way the region I built, where I can trust everything is convex or quadratic. And there are several ways of playing with this. The 11-layer Marquardt somehow increases the region or decreases with the lambda. But there are other ways of computing regions as well. Like one is, too much details. But if you want to get more information on that, you can just go on Wikipedia and look for trust region methods. And you will find a lot of other techniques there. Any further question? Okay, almost done. So when we do this landmark-based graph-based LAM with landmarks. They're not new, they're not just for the SLAM community. People in photogrammetry especially, they've done it for 3D cases, where basically you add some observation towers. They want to build a map of the world. They had some observation towers, they had some cameras, they were measuring the angle between different observation towers, triangulating them and trying to build a map of the whole Earth. And there was already during the 50s a lot of methods for matrix factorization, multiplication, like Cholesky decomposition and so on, have actually been invented during this period for that specific problem. Gauss was also working a lot in photogrammetry, and also the Gauss-Newton method was invented during that time for solving this kind of problems. But how they're called is they're called bundle adjustment. The name comes from the fact that if you have a lot of poses, so camera poses for them, and some landmarks, there is a lot of lines that connects each poses with the landmark that are all observing, and this is like a bundle of threads, and they want to adjust the bundle to make sure that all the reprojected error on the landmark will be as small as possible, okay? And by reprojection error means I'm here, I have my camera, I'm observing these things on this pixel, and now I get the full state. I take the real estimate of the landmark, I put it back on my camera, and I want to minimize the pixel distance between where I'm seeing the landmark right now and where it is projected in my camera, okay? So that's what it means by minimizing the reprojection error. It's a different cost function, but in principle it's the same as we've seen before. The only thing you have to change is how you compute the error function. But at the end, it's again a nonlinear least squares problem that gets solved with Levenberg-Marquardt most of the time, or some more complicated or more advanced way of finding a solution for the least squares problem. Okay? So summary of this part. I've shown you how you can use the graph-based line formulation when we also consider landmarks and not only robot poses. You got a bit of an idea or intuition how Hessian actually changes according to different measurements and why it matters, what are the consequences, and how you can play with that. And show that one way of make sure that we have a Hessian which is always full rank is to use other algorithms like Levenberg-Marquardt for optimizing and for solving the least squares problem. An interesting read, it's this paper from Bill Triggs and some other people. It's called Bundle Adjustment and Modern Synthesis. It's, I think, about maybe 40 pages. It's quite big. It's like a chapter of a book. But that gives you a lot of information also on a lot of small details, like how to tune parameters, how to handle data association problems, how to make data association, how to speed up convergence, and so on. So it's a very nice read if you have some time to spare and are interested in minimization problems or geometric problems with landmarks and robot or camera poses. That will be it for today, and if there are any questions, just ask, otherwise you can finish.